Hello, good evening everyone. Friday, once again, we are meeting at 8 o'clock. You are enthusiastic to learn thermodynamics. I am also enthusiastic to help you to learn thermodynamics. At the outset, I would like to thank Ekeeda for creating this opportunity to reach students in this way. I request everyone to buy Ekeeda videos. Okay, in this live session, I am going to discuss properties of pure substance and some of the problems on this pure substance. So before going to the actual topic, I would like to tell one thing that if you get any questions, you may post in the chat box chat, so that I will read those problems and I will resolve those problems here itself. If you get any problems after 9 o'clock, that is beyond this live session, you may post a WhatsApp message to the number which is available on the screen. So I will solve, or I will try to answer those questions through WhatsApp message only. So all of you buy Ekeeda videos. Here I briefly discuss about properties of pure substance, and then I will directly move on to these problems. Okay, I would like to start with definition of pure substance. A pure substance is a substance which has uniform chemical composition and physical structure throughout its mass. So some of the examples of pure substance is water, and then oxygen, and there are different pure substance. We are more interested in pure substance, that is water, because which is widely used as a working substance in case of thermal power stations, where that working substance, that is water, that will continuously receive heat from the boiler, or else from the furnace in the boiler, I can say, in the furnace in the boiler, and changes its phase from liquid to vapor, and that is expanded in the turbine, and that will produce work, and then the low pressure steam that comes out of the turbine, and that gets condensed. In the case of condensation, its phase transformation takes place from vapor to liquid, and then once again it is pumped back to boiler, and in the boiler once again that working substance water receives heat and changes its phase from liquid to vapor, and that cycle repeats. Here in these properties of pure substance, I am going to discuss how exactly and at what pressure and what temperature their properties gets changed, and their property values at different temperatures and pressure are listed on table. I will show that table also, and the table is called as thermodynamic data table, and that book is called as thermodynamics data handbook, and I will explain that one also in detail in this live session. Before going to that, let us start with water, which is present at the atmospheric temperature and atmospheric pressure. The water which is at atmospheric pressure and room temperature, it may be around at 25 degrees Celsius, it may be at 25 degrees Celsius, and 1 atmospheric pressure. That 1 atmospheric pressure means it is 101.325. This is when that 1 atmospheric pressure is converted into kilopascals, it is 101.325 kilopascals. If heat is added to water which is at 25 degrees Celsius, its temperature rises. So the water which is at 25 degrees Celsius, which is at a state of subcooled liquid or compressed liquid, it is a subcooled liquid, or it is also called as compressed liquid. When it is heated, as I already told you, its temperature rises, and at 50 degrees Celsius and 1 atmospheric pressure, it is once again, it is at a state of subcooled liquid. Okay, and if it is heated again, and when it reaches a temperature of 100 degrees Celsius at 1 atmospheric pressure, I am mentioning that at 1 atmospheric pressure because I will tell you that one when it comes to that table. At 1 atmospheric pressure, at 100 degrees Celsius, it starts boiling. I hope you have studied that boiling in your science of your high school education, where water gets boiled at 100 degrees Celsius. Boiling means when it is boiled, it starts its changing phase from liquid state to vapor state. The boiling, when it is boiled, you can see water converted into vapor phase. So at 100 degrees Celsius and at 1 atmospheric pressure, it starts changing its phase from liquid to vapor, and water at 100 degrees Celsius, it is called as saturated liquid. It is called as saturated it is called as saturated liquid. If heat is added beyond this, it starts changing its phase. That is why it's called as saturated liquid, and that is the last point as a complete liquid. So as I already told you, it starts changing its phase from liquid to vapor state. So during that heat addition will be there, but there will not be change in temperature, and that a change in phase take place at constant temperature and constant pressure. So that takes place during that time. So initially it will be more percentage of liquid and less percentage of vapor, and at the middle there will be 50% liquid and 50% vapor, and upon adding that heat, finally it is completely vapor, 100% vapor and 0% liquid, and that state is called as saturated vapor. It is called as saturated vapor, and at that point, that is completely changed. That water in the liquid phase is completely changed into vapor, and that is called as saturated vapor state. And if heat is added beyond that point, then its temperature once again starts rising, and that state of the pure substance is called as superheated vapor. I will explain this phase change with the help of a graph. Uh, in that graph we will have enthalpy and entropy. Along y-axis let's have specific enthalpy. Along x-axis let's have specific entropy. Now let us take the state point 1. State point 1, it is water at 25 degrees Celsius, at 125 degrees Celsius. When it is heated, its temperature increases and its enthalpy also increases. Its enthalpy also increases. Then at constant okay, it's not let us take it as temperature enthalpy diagram. Let us discuss HS diagram later. It is temperature entropy diagram. So when it reaches 100 degrees Celsius, it is 100 degrees Celsius and 1 atmospheric pressure. This is called as saturated liquid state. This is saturated liquid state. At this point, it starts changing its phase from liquid to vapor. So at this point, there will be more quantity of water in the liquid state and less quantity of vapor state. And at the center, as I told you, it is 50% water in the liquid phase and 50% in the vapor phase. And maybe at this point it may be 90% vapor and 10% in the liquid state. And at this point it is 100% vapor. At this point it is 100% vapor and 0% liquid. So this point is called as saturated vapor state or dry steam, right? Dry steam, it is called as dry steam. That means it does not have any wet content. So this phase transformation takes place at a constant temperature, and if heat is added beyond this point, its temperature once again rises, that is above 100 degrees Celsius, maybe up to so many very high temperature, maybe 500, 600. We'll just take it as 200 degrees Celsius. It is at 1 atmospheric pressure, and if the same thing happens at 5 bar, the curve may be like this, and if the same thing happens at 10 bar, the curve may be like this. And if we join these saturated liquid lines, see, these are saturated liquid lines, right? Saturated liquid lines. And if we join saturated vapor line after that, we will have a curve like this. Let us take this point somewhere here. Okay, we will have a dome shaped curve. So left to this curve, it is completely liquid, and within this curve, it is liquid plus vapor, and right to this curve, it is only vapor, and the point at the topmost point, it is called as critical point, it is critical point. That means at this point water in the liquid and vapor, that what is water will be directly converted in the liquid state is directly converted into vapor state at this point. So as I told you, before this it is liquid phase, and that is left to this curve is liquid phase, and right to this curve is vapor state, only vapor, and in between this it is liquid plus vapor. And as I already told you, the pure substance, that is water, in this region it is a subcooled liquid or compressed liquid, and that water in this region, it is a wet steam. As I told you, it is wet steam, and water in this, it is completely dry steam. It is completely dry, there is no wet content. So I'll repeat once again, here it is only in the liquid phase, and in this region it is liquid plus vapor, and in this region it is completely dry. Now let us have a TH diagram. T and H diagram. Here we will have a water which is at 25 degrees Celsius, and if heat is added, its enthalpy increases as well as its temperature increases, and at saturated liquid state, when heat is added, definitely its heat content, that is enthalpy, increases, and it takes place at a constant temperature. And this point, as I already told you, it is saturated liquid state, and this point it is saturated vapor. It is completely dry. It is that means it has a dryness fraction of 1, and if it is heated again, that is superheated steam. Now let us have a few simple things for this. From its initial to its saturated liquid point, it is called as HF, and from during this phase change, that increase in enthalpy, that is denoted by HFG, and this total, that is from initial to dry saturated point, it is called as Hg, and at this point it is H superheated. So HF is enthalpy of the saturated liquid, and HFG is actually called as latent heat of vaporization. That is the heat that is required to convert its phase from okay, it is latent heat of vaporization. So addition of that heat will change its phase from liquid to vapor, that is called as enthalpy of vaporization. The total heat that is required to have a saturated vapor is called as Hg. So here Hg is equal to Hf plus HFG, And now, if that particular steam is wet steam, let us assume it is heated up to here and it is stopped here, but there are some content of wet, there is some wet content. In that case, uh, it will have we will have a concept called dryness fraction. The dryness fraction is the fraction, that is the amount of vapor present in the wet steam. So that is denoted by usually X. So in that case, enthalpy of wet steam will be HF plus X into HFG, X into HFG, enthalpy of wet steam. Okay, and now let us see what are these values, how exactly we can get these values for different pressures. For that, we will have a table from the thermodynamic data handbook. I will discuss that one. See here, we have thermodynamic properties of saturated water and dry saturated steam. In this table, we can have property values of saturated water and dry saturated steam. Here we will have different properties. The first column, there is pressure, and the second column is saturated temperature. The third column is specific volume of VF means specific volume of saturated water. VG is a specific volume of saturated steam or dry saturated steam. Here HF is enthalpy of saturated water. HFG is latent heat of vaporization, and then Hg is enthalpy of dry saturated steam. Here you can observe HF plus HFG will be Hg. You can add these two values, we will get these values. HF plus HFG is Hg. So as I already told you, HF is enthalpy of saturated liquid. HFG is latent heat of vaporization. Then Hg is enthalpy of dry saturated steam. Then SF is entropy, specific entropy of saturated liquid, saturated water. Then HFG is the entropy of latent heat of entropy during vaporization. Then the Sg is entropy of saturated vapor. So here we will have these values at different pressures. At different pressures, we can have these values. The first table, we will have data on different pressure, and in the next table, that is in the second table, we will have data on the saturation temperature. So first column is saturation temperature and second column is pressure. So we will have those values, and I will tell you how to take values from this data handbook or this table while solving the problem. And the next table, we will have see here, see properties of superheated steam. In the previous two tables, we had data that is property values of saturated liquid and saturated vapor. Here we have data of superheated steam. So it is beyond, when heat is added beyond dry saturated state, we will have superheated steam. So these are the property values of superheated steam. Here we have absolute pressure in this column, and V is a specific volume, H is specific enthalpy, S is specific entropy, and we will have values at different temperatures. So for superheated steam, we will always have pressure and temperature. So that is how we can differentiate the saturated steam and superheated steam. So this is the table from which we will take data to solve problems. So I will take the first problem, and if you get any questions, you may ask. So I will start with the first problem. The first problem I have taken like this. Determine the amount of heat which must be supplied to 2 kg of water at 25 degrees Celsius to convert it into steam at 5 bar and 0.9 dry. So that means here it is not a dry saturated steam, it is a wet steam, because dryness fraction is 0.9. If the dryness fraction is 1, it is dry saturated steam. If the dryness fraction is 0, it is saturated liquid. And if the dryness fraction varies from 0 to 1, it is wet steam. Okay. While solving the problems, you will understand better. Let me start this one. So here once again we have 2 kg of water. So that mass is 2 kg. Their mass is 2 kg, and its temperature at state point 1 is 25 degrees Celsius. Now, when heat is added, its pressure increases to 5 bar, and its dryness fraction will be 0.9. That is at state point 1, T1 is 25 degrees Celsius. It is 25 degrees Celsius at state point 1. Now it is 5 bar, that is pressure P2 is 5 bar, and its dryness fraction X is 0.9 at state point 2. See, let's see how exactly this will have. So for that, let's have a temperature versus enthalpy diagram, TH. It is temperature versus enthalpy. As usual, we will have a dome shaped curve, and here water which is at 25 degrees Celsius. So if it is heated, that will be converted into 5 bar and 0.9 dry. See here, it is 0.9 dry. It is not reaching this dry saturated curve. So it is stopped at here only. It is 0.9 dry. That's why it is X. So this is state point 1, and this is state point 2. So here the enthalpy of wet steam HW is equal to HF2 plus X into HFG2, right? So this is the enthalpy of the wet steam at state point 2, and here we should determine the heat which must be supplied to 2 kg of water at 25 degrees Celsius to convert it into steam at 5 bar and 0.9 dry. So what is the heat that must be applied? According to the first law of thermodynamics, that is applied to a closed system that has been discussed, that Q is given by m into H1 minus H2, and it has been discussed while discussing the first law of thermodynamics applied to a closed system undergoing a processes. Yes, please post your doubt, Mr. Venkat Sai. Please type your doubt and send me. I am here to clarify. Okay. So here H1 is the enthalpy of the steam at state point 1, and H2 it is HW, that is H2 is equal to HW. Now first let us take what exactly this H1. So at state point 1, as I already told you, it is at 25 degrees Celsius. It is just a subcooled or compressed liquid. So the property value of that is HF. So what is that? It is at 25 degrees Celsius. What is the value of HF that is to be taken? So for that, let's go to the second table. It is on the temperature basis. Table 2, right? So what is the temperature? It is 25 degrees Celsius. See, at 25 degrees Celsius, okay, at 25 degrees Celsius, what is this HF? HF is 104.8 degree, 104.8 kilojoules per kg. So at state point 1, it is H1 is equal to HF1, that is equal to, what is that value at 25 degrees Celsius? It is 104.8 kilojoules per kg. One hundred 4.8 kilojoules per kg. Okay, that is H1. Now H1 is calculated. As I already told you, to find out H2 is enthalpy of wet steam, as it has already been told. It has a drainage fraction of 0.9. So at state point 2, let us take the data from data handbook, that is at state point 2, that is at 5 bar. At 5 bar. So now let us take what is the value of HFG at 5 bar. I need HF and HFG to find out enthalpy of wet steam, that is equal to enthalpy at the final state. So it is on the basis of pressure. Okay, So this is on the basis of pressure. So it is at 5 bar, right? It is at 5 bar, right? It has been told it is at 5 bar. What is HF at 5 bar? Uh, it is 640.1 kilojoules per kg. So HF2, it is 640.1 kilojoules per kg. Similarly, HFG2, HFG2 at 5 bar, HFG2 is 2107.4 2107.4 kilojoules per kg. Now we have HF2 and HFG2. Now to find out H2, we have the formula like this. H2 equal to HW is equal to HF2 plus HFG2. So HF2, it is not simply into X, it is X into HFG2 because it is a wet steam. So HF2 is 640.1, it is listed from this one, plus HFG2, it is 2107.4 into X, it is 0.9. So this value, let us calculate this value, then that becomes 2536.76 kilojoules per kg. Now H1 is calculated, H2 is calculated, we have mass M. From that, let us find out Q. So as it is already been written, Q equal to M into H2 minus H1. So here M, that mass is 2 kg, so it is 2 into 2536.76 minus H1 is 104.8. So this value becomes 4863.98 kilojoules. It is not kilojoules per kg, it is simply kilojoules, because to this kilojoules per kg, if mass is multiplied, that kg get cancelled. So there has to be 4863.98 kilojoules of heat must be supplied to take the water at 25 degrees Celsius to 5 bar and 0.9 dryness fraction. So that is the heat it is calculated. So if you have any questions, you may post that question here. I will solve those questions. Okay, please, Mr. Venkat Sai, if you have any question. I really appreciate if you ask questions. That means you are following that. They are definitely better than the students or those who make some unnecessary comments. useless comments. Okay, after this, I'll go to the next problem. Okay, here steam at 10 into 10 power 5 Newton per meter square means it is 10 bar. It is simply 10 bar, and 0.95 dryness is available. Find the dryness, final dryness fraction of steam if 9.56 kilojoules of heat is removed per kg of steam at constant pressure. That means if 9.56 kilojoules of heat is removed per 1 kg of steam, then what is the final dryness fraction? That is the question. So initially at state point 1, at initial state, the pressure P1, it is 10 into 10 to the power 5 Newton per meter square. That means it is 10 bar, because 1 bar is 10 to the power 5 Newton per meter square. It is 10 bar, and its initial dryness fraction, let us take it as x1, it is 0.95. Find the final dryness fraction of steam. So that is what is x2, and it happens at a constant pressure. P2 is also 10 bar. So for that, let us find out what exactly what the H1, that is enthalpy of wet steam. So that enthalpy of wet steam H1 is equal to HF1 plus X1 into HFG1. So now let us have these HF1 and HFG1 at 10 bar from the data handbook. So from data handbook, at 10 bar, let us have HF1 and HFG1. So let us have these values. So it's once again on the pressure basis. So it is 10 bar. HF1 is 762.6 kilojoules per kg. See here at 10 bar, it is HF, right? HF is the enthalpy of the saturated liquid. It is enthalpy of the saturated liquid. So it is 762.6 kilojoules per kg. Similarly, HFG1. So at 10 bar, this is HFG. It is 2013.6 kilojoules per kg. It is 2013.6 kilojoules per kg. Now let us find out the enthalpy of the wet steam when it is 0.95 dry. So HF1 is 762.6 plus X1 is 0.95 into HFG1. It is 2013.6 kilojoules per kg. So H1 will be 2675.52 kilojoules. So this is the enthalpy of the wet steam at 10 bar when its dryness fraction is 0.95. Now, as I already told, if heat is added, its dryness fraction increases. Finally, it becomes 1. Then it becomes dry saturated steam. At the same time, if heat is removed, its dryness fraction decreases, right? So in such a case, if 9.56 kilojoules of heat is removed from this wet steam, if 9.56 kilojoules of heat is removed from this wet steam, which is 0.95 dry, what will be its final dryness fraction? So if heat is added, dryness fraction will be increased. If heat is removed, dryness fraction will be decreased. So if that 9.56 kilojoules of heat is removed, we have this formula Q is equal to H1 minus H2, right? So from this H1, if that Q that is 9.56 kilojoules of heat is removed, what will be H2? In that case, this H2 will be H1 minus Q. So here H1 it is 2675.52. It is 2675.52 minus Q, that is it is 9.56 kilojoules of heat is removed. Then this value becomes 2666.52 kilojoules. When that amount of heat is removed at that constant pressure, that enthalpy of wet steam becomes this one. Then we can find out this dryness fraction using this formula, that is H2 is equal to HF2 plus X2 into HFG2. Here, what are the values of HF2 and HFG2? HF2 and HFG2 are same as HF1 and HFG1, as it is happening at constant pressure. Since it is happening at constant pressure, so HF2 and HFG2 are also same. It is HF2 is equal to HF1 and HFG2 is equal to HFG1. So we have this H2. Let us substitute these values, and from that we can find out its final dryness fraction. As I already told you, if heat is removed, its dryness fraction decreases. If heat is added, its dryness fraction increases. So H2, it is already calculated in the previous step. It is 2666.52, that is equal to HF2 is equal to HF1. It is 762.6 plus X2 into HFG2 is equal to HFG1. It is 2013.6. So we will have a final dryness fraction of X2 is equal to 0.9455. So its dryness fraction is decreased from 0.95 to 0.9455 when there is an heat removal of 9.56 kilojoules. So this is another problem. I have solved two problems in this live session along with the basic points of pure substances. If you have any questions, you may ask those questions, and I will clarify. And if you get any questions after this, you can post or you can send that question to the WhatsApp number which is there on the screen, So for all theory concepts by Ekeeda videos, I all of you buy Ekeeda videos only, so that is more informative. Those videos have good conceptual contents. So I kindly request you to buy Ekeeda videos, and I will wait for another 2 minutes. If you have any questions, you may post. Yes, questions are welcome. Okay, with that, I am ending this live session here. Let us join in the next live session, which is on next Friday at same 8 o'clock. Okay, thank you for joining.